We are in section 7.8, Improper Integrals. In this section, we extend the concept of a definite integral to the case where the interval is infinite, and also the case where f has an infinite discontinuity in our interval from a to b. So the first type that we have is an infinite integral, and it says to consider the infinite region S that lies under the curve y equals 1 over x squared above the x-axis and to the right of the line x equals 1. You might think that since S is infinite, to extend, the area must be infinite. However, this is not true. In fact, the area of part of S that lies to the left of the line x equals t, a of t is equal to the integral from 1 to t of our function, which is 1 over x squared dx. And so rewriting that, we're able to integrate it and then evaluate it from 1 to t. And when we do, we arrive at a function that's going to be 1 minus 1 over t. Notice that our area is less than 1, no matter how large t is chosen. Moreover, since the limit as t approaches infinity, so as that goes off towards the right, of our area is going to just equal 1. So we can say that the area of the infinite region S is equal to 1. And we write, and this is our key part here with the notation, it's going to be the integral from 1 to infinity of 1 over x squared dx. However, you're not able to evaluate an integral at a value of infinity since it's not a numerical value. And by our fundamental theorem of calculus, we know that it has to be a numerical value. So we're going to rewrite this using the limit and say the limit as t approaches infinity of the integral from 1 to t of our function is equal to 1. And so you can see down here what happens as t gets farther and farther and farther away from 1. And that area from 1 to infinity would equal 1. And as it goes, it gets larger. These types of integrals arise a lot in different types of application problems. So we have convergent and divergent. So convergent is an integral is said to be convergent if the integral has a value that is a real number, and it's divergent if an integral is not convergent, then it's divergent. A divergent integral does not have a value of a real number, usually because the area under the curve is infinitely large. So improper integrals of type 1, infinite integrals, there's 3 different types we're going to look at here. So the first one says A. If the integral from a to t of f of x dx exists for every number t greater than or equal to a, then the integral from a to infinity of our function is equal to, and what we have here, if we draw this, is saying that we have a function, and I'll say this is a, and we'll say from a onwards to infinity, this area under our curve is going to be equal to the limit as t approaches infinity of our integral from a to t of f of x dx, provided that the limit exists as a finite number. Likewise, case B says if we have an integral from a to t of f of x dx exists for every number t less than or equal to b, then our integral from negative infinity to b of f of x dx is going to equal, and we're going to have the limit as t approaches infinity of our integral from t to b of f of x dx, provided this limit exists as a finite number. And so for this, we would have another graph, and this time as it goes off to negative infinity, and we would have a value, we'll say b, and so this area down here we'd be able to find. Part C says if both the integral from a to infinity of f of x dx and negative infinity to a of f of x dx are convergent, Then for any real number a, we define the integral from negative infinity to positive infinity of our function f of x dx equal to the sum from negative infinity to a of f of x dx plus the integral from a to infinity of f of x dx. So in order to evaluate this and find this, we're going to now use parts a and b that we did on the previous page. So then use parts A and B to evaluate. And also a little side note here that if any one of these integrals is going to be divergent, then the whole entire integral, the original integral, would be divergent also. So the next thing we have is a definition. This is a great one to know. It says the integral from 1 to infinity, and it doesn't necessarily have to be 1 as your lower limit, but from a number out to infinity of 1 over x to the p dx is convergent if p is greater than 1, and divergent if p is less than or equal to 1. This is a nice time saver for certain problems. It's very specific though. It's x to the p, so x to some value, and if p is greater than 1, it's convergent. If it's less than or equal to 1, then it's divergent. The example says, determine whether each integral is convergent or divergent. Evaluate those that are convergent. So the first one we have says, evaluate the integral from 0 to infinity of 1 over the 4th root of 1 plus x dx. So in order to do this, we're first going to rewrite this with a limit and say the limit as t approaches infinity of 0 to t of 1 over the 4th root of 1 plus x dx. And so from here, I'm going to use u sub and say let u equal 1 plus x. This way I can evaluate this integral. And then du is equal to dx. I also need to change my limits of integration, so we'll make sure we do that. And also don't forget to write limit every single time. If you forget the limit part, it's technically incorrect. So we're going to have the integral, and I'll change those limits of integration in just a moment. And this was the same as 1 minus x to the negative 1/4 power, or u to the negative 1/4 power, du. And our upper limit of integration is going to be 1 plus t, and our lower limit is going to be 1 plus 0, or just 1. So putting those both on. And from here, I can integrate, and again, keep writing the limit. We haven't evaluated the limit yet, but it's going to now be u to the 3/4 times 4/3. And again, we're evaluating this from u equals 1 to, and I'm going to rewrite that as t plus 1. And so now evaluating this using our fundamental theorem of calculus, we're going to have the limit as t approaches infinity of 4/3 t plus 1 to the 3/4 minus 4/3 times 1 to the 3/4. And so now we have the limit on each of these, but notice that your second term here is just a constant value, so taking the limit of that would just be that constant value also. We learned that back in Calc 1. And so we have the limit of 4/3 of t plus 1 to the 3/4 minus 4/3. And so right here, this limit, if you were to evaluate this limit, this is going to be infinite, so this is going to diverge. And so our integral, the original integral up there, is going to be divergent. It diverges. The next example says find the integral of 1 to infinity of 1 over 2x plus 1 to the 3rd dx. And so in order to do this again, we're going to rewrite this with a limit. So we have the limit as t approaches infinity, and you can use any variable you want, and it's going to go from 1 to t of our function, which is, I'm going to rewrite this as 2x plus 1 to the negative third dx. And now to evaluate this and to integrate this, I'm going to use u sub again. So I'm going to let u equal 2x plus 1, and then du is going to be 2 dx. Make sure to continuously write your limit as t approaches infinity. And then this is of 1/2. We do need to change our limits of integration. We'll do that momentarily. And it's going to become u to the negative third du. Our upper limit of integration is now going to be 2t plus 1. And our lower limit, when we plug in 1, is going to work out to being 3. So lower limit's 3, upper limit is going to be 2t plus 1. So from here, we have the limit as t approaches infinity of 1/2 times, and now integrating this, we get u to the negative second times 1 over negative 2. And we'll evaluate this from u equals 3 to 2t plus 1. And so we still have the limit as t approaches infinity of, and this is going to become negative 1 over 4u squared, evaluated from u equals 3 to 2t plus 1. And now we use the fundamental theorem of calculus and evaluate this. Again, continuously write that limit until we evaluate the limit. So we have the limit as t approaches infinity of, and we have negative 1 over 4u squared, which is 2t plus 1 squared, minus, and then evaluating this at 3, we're going to have negative 1 over 4 times 3 squared. And so the limit goes to both of these, gets distributed in. However, that second term is just a constant again, so the limit doesn't matter. The limit of a constant is just that constant. And so we have negative 1 over 4 times 2t plus 1 squared plus, and that's going to be 1 over 4 times 9, or 1 over 36. And then looking at our limit this time, because t is going off to infinity, 1 over an infinite large number is going to be approaching 0. And so that means that this is going to be 0 plus the 1 over 36. And so this equals 1 over 36. Since this is a numerical value, we can say that this is going to be an integral that's going to converge. Part C, the next integral that we have, says evaluate negative infinity to 0 of 2 to the x dx. So the same idea, but this time we have the limit as t approaches negative infinity of the integral from t to 0 of 2 to the x dx is equal to, and this is going to be the limit as t approaches infinity of, and integrating this, we don't need to use any type of substitution, so this is just going to be 2 to the x all over ln of 2. And we're evaluating this from x equals t to 0. So we're going to have the limit as t approaches negative infinity of, and then evaluating this at our upper limit, we're going to have 2 to the 0 over ln of 2 minus 2 to the t over ln of 2. And so first one this time is our constant, so we end up with 1 over ln of 2 minus the limit as t approaches negative infinity of 2 to the t all over ln of 2. And so the limit, as we evaluate this, if you remember, 2 to the t would look something along these lines. And so as it goes off to negative infinity, it's getting closer and closer and closer to 0. So this is approaching 0 here. So we're going to have 1 over ln of 2 minus 0, or just 1 over ln of 2. And so since this is a numerical value, this converges. The next example says find the integral from negative infinity to negative 1 of 2x minus 1 over x squared minus x dx. So I'm going to go ahead and first rewrite this with the limit. Say the limit as t approaches negative infinity, the integral of t to the negative first of 2x minus 1 over x squared minus x dx equals, and so in order to integrate this though, we're going to have to do something to this integral. I'm going to go ahead and try u sub. I'm noticing that the denominator of x squared minus x, the derivative of that is equal to the numerator. And so let's try letting u equal x squared minus x. Then du is going to be 2x minus 1 dx. And so our limit of t approaches negative infinity of our integral is now going to become 1 over u du. And so we have to now change our limits of integration. And so our upper limit of integration is going to be negative 1 squared minus negative 1, which works out to being 2. And then our lower limit of integration is going to be t squared minus t. And we can integrate 1 over u. So don't forget to continuously write the limit until we evaluate that. And integrating this, we get the natural log of the absolute value of u. And we're evaluating this from u equals t squared minus t to 2. So then evaluating this, we have our upper bound, which is going to be ln of the absolute value of 2, which is just 2, minus ln of the absolute value of t squared minus t. And then taking the limit of each of these, the limit as t approaches negative infinity of ln of 2 is just going to become ln of 2, minus the limit as t approaches negative infinity of ln of the absolute value of t squared minus t. And so now looking at this, we know that our log functions look something along these lines. So as we approach negative infinity, this is going to go down to negative infinity also. So this is going to go to negative infinity, or it diverges. And so this is going to diverge. Therefore, that integral that we had is going to diverge also. The example right below it goes from negative infinity to positive infinity. So I'm going to go ahead and circle E, and we'll work on that one together in class. At the top of the next page, we have improper integrals of type 2. These are discontinuous integrands. They're going to have vertical asymptotes, and so there's going to be a restriction in the domain. So there will be a restriction in the domain. It's caused by a vertical asymptotes. This is usually going to be zeros in the denominator. So maybe a 0 in the denominator if you're dealing with rational functions. So we'll say with rational functions. We also have these kind of issues with vertical asymptotes with exponential or logs. So we'll say exponentials or logs. And so part A says if f is continuous on our interval from a to b, where a is included and b is not, and discontinuous at b, then we're able to rewrite this as the limit as t approaches negative infinity of ln of 2 minus the limit t approaches b from the left of a to the t of f of x dx, if the limit exists as a finite number. So looking at a picture of this would be where we have a function and maybe we have a vertical asymptote that's occurring here, and we'll put a dashed line to represent that, and that's going to occur at b. And so we go from a to b. We're going to be approaching b from the left side, and so I'll go ahead and say here's t. And so we're able to use this to approximate that, or to determine that area under that curve. Part B says if f is continuous on the interval from a to b and discontinuous at a, then we're going to have the integral from a to b of f of x dx is going to equal the limit as t approaches a from the right of our integral from t to b of f of x dx. If this limit exists as a finite number, and so again, this time we're going to have a vertical asymptote at a. So drawing that on, there's a going out towards b, and here's t, and we're approaching a from the right, and this will be able to find that area under that curve. Likewise, the improper integral from a to b of f of x dx is convergent if the corresponding limit exists and divergent if it does not exist. We also have c, which says if f has a discontinuity at c, where c is in between a and b in that interval, and both the integral from a to c of f of x and the integral from c to b of f of x dx are convergent, then the integral from a to b of f of x dx is going to equal the integral from a to c of f of x dx plus the integral from c to b of f of x dx. And then we would use parts A or B up above. And so looking at a picture of this is again where we would have from A to B. C is going to be somewhere in the middle, and that's where it's discontinuous, meaning that's going to be where we have a vertical asymptote, and that means that from A we have going towards that vertical asymptote, and likewise for B going towards that vertical asymptote. And so we can split this and find the limit as you're approaching it from the left and from the right of each of these, and then sum them together. The next example says determine whether each integral is convergent or divergent and evaluate those that are convergent. So part A says the integral from 2 to 3 of 1 over the square root of 3 minus x dx. So these types of problems don't stand out because they don't have a lower or upper bound of infinity or negative infinity. However, if you look at this, since we do have a rational function here, it is going to have an issue where the denominator is equal to 0. And so we know that 3 minus x cannot equal 0, which means that we have a vertical asymptote at x equals 3. And so we would have the limit as t approaches 3 from the left of the integral from 2 to t of 1 over the square root of 3 minus x dx. And so to integrate this, we're going to let u equal 3 minus x, du equal negative dx. And so our limit is now going to become limit as t approaches 3 from the left of our integral, which is going to be our new upper limit is going to be 3 minus t, and our new lower limit is going to be 3 minus 2, or 1. So from 1 to 3 minus t of, and I'm going to rewrite this as it's the 1 over the square root of 3 minus x, and that's the same thing as saying 3 minus x to the negative 1/2, or u to the negative 1/2 du, and it is negative. I'll put the negative in front of our integral. So first thing we write is limit as t approaches 3 from the left, Integrating this, we get negative 2u to the positive 1/2. Evaluate from u equals 1 to 3 minus t. So we have the limit as t approaches 3 from the left of, and we have, evaluating this at our upper limit, we have negative 2 times 3 minus t to the 1/2 minus, and then evaluating this at 1, we're going to have negative 2 times 1 to the 1/2. And so we're going to have the limit as t approaches 3 from the left of negative 2 times the square root of 3 minus t, and then plus positive 2. And if we look at the limit that we have here, you'll notice as you're approaching 3 from the left, it's going to become 3 minus 3, which is 0, times negative 2, which is also going to be 0. And so we end up with, so that's going to converge to 0. So 0 plus 2, which is 2. And so yes, this converges. Part B says find the integral from 6 to 8 of 4 over x minus 6 cubed dx. Again, notice that x cannot equal 6, makes the denominator be 0. So that means that we're going to have a vertical asymptote at 6. And so that is an issue here. And so we're going to rewrite this as the limit as x approaches 6, and this time we're on the right, so I'll put a plus sign there, and we're going to go from t to 8 of, and this is the same thing as 4 times x minus 6 to the negative 3rd dx. And so to integrate this, we're going to let u equal x minus 6 and du equals dx. We'll change those limits of integration momentarily, but don't forget to write limit. And we're going to have 4 u to the negative 3rd du. And your lower limit of integration and your upper limit of integration are going to change. So we're going to have 8 minus 6, which is 2. And then our lower is going to be t minus 6. So from t minus 6 to 2. So we can integrate this. Don't forget to write limit. And so integrating this, we have 4 times, and this is going to become u to the negative 2 times negative 1/2. And we're going to be evaluating this from u equals t minus 6 to 2. And so we get the limit as t approaches 6 from the right. And then rewriting this, we get negative 2 over u squared. Again, a value from u equals t minus 6 to 2. So we're going to have the limit as t approaches 6 from the right of, and the first thing I'm going to evaluate is at 2. So we have negative 2 over 2 squared minus, and then we have negative 2 over t minus 6 squared. And so the constant just stays a constant, and so that's going to become negative 1/2. Then we have plus the limit as t approaches 6 from the right of 2 over t minus 6 squared. And so looking at our limit, you will notice that as we get closer and closer to 6 on the right, our denominator is going to approach 0. And we have 2 over 0, which means that this is going off to infinity, or it diverges. And so that means that our whole entire integral is going to diverge. So the next example that we have, I'm going to go ahead and circle, and we'll look at that one together in class. The next example says sketch the region and find the area if the area is finite. The region is S, and it is all the points x, y such that x is less than or equal to 0, and y is going to be greater than or equal to 0, and less than or equal to e to the x. So let's go ahead and sketch the region. And so if I were to graph e to the x, goes on, but here is on, first thing says x is less than 0, so I'm only looking at the left of it from the vertical axes. And then it says that y is greater than 0, so it's above your y-axis, smaller than your y-axis, so x is less than 0. And then it says y is less than our function. So we are looking for the shaded area in here. So our area is going to be from negative infinity to 0 of e to the x dx. And so we can't evaluate this. We do need to write limit. I'll say as t approaches negative infinity of t to the 0 of e to the x dx. So this is now be the limit as t approaches negative infinity of e to the x, evaluated from, as we integrated that was just e to the x. So we say from x equals t to 0. So we have the limit as t approaches negative infinity. And so evaluating this, we have e to the 0 minus e to the t. And so we get e to the 0, which is just going to be 1, minus the limit as t approaches negative infinity of e to the t. And so we have 1 minus, and so as you think of your exponential, as it goes off to negative infinity, you can see in the graph, this is approaching 0. So we have 1 minus 0, which is just 1. And so yes, this does converge. The last thing that we have in this section is called the Comparison Theorem. And this says, suppose that f and g are continuous functions with f of x greater than or equal to g of x, which is greater than or equal to 0, for x greater than or equal to a. So the first one says, if the integral from a to infinity of f of x dx is convergent, then the integral from a to infinity of g of x is also convergent. And the reason why is because, and we'll sketch a little graph over here, it says that f and g are going to be continuous functions, and f is greater than g. And so we know that if f is going to be converging to some kind of number, we'll say that it's approaching a number here, we'll call this f of x, then g of x, which is less than it, is going to be forced to be convergent also to some number. Also remember that g of x is greater than 0. So likewise, part B says that if the integral from a to infinity of g of x dx is divergent, then f of x is also divergent. So again, sketching a picture, we'll say that if g of x is divergent, so it diverges off, it's g of x, that is going to force our function f to diverge also. So the example right below it says use the comparison theorem to determine whether the integral is convergent or divergent. So for the first problem here, we have the integral from 1 to infinity of 2 plus e to the negative x over x dx. And looks pretty difficult to integrate, so I would say that since e to the negative x is always going to be greater than 0 for our interval, which is from 1 to infinity, so we'll say for all x greater than or equal to 1, we can say that 2 plus e to the negative x over x would be greater than, just a simplified version of this is just 2 over x, and that's because e to the negative x is always going to be greater than 0, so that value would be, that expression would be larger than just 2 over x. And so up above, using the comparison theorem, it says that f of x and g of x, where f of x is greater than or equal to g of x. So I'm going to call this first one f of x since it's greater, and the second one g of x since it's less. And so I'm going to go ahead and take my g of x, which is now going to become, and I'm going to integrate it from 1 to infinity. So this is going to be 2 over x dx. And we can say that this is now going to be the limit as t approaches infinity of the integral from 1 to t of 2 over x dx, which is going to now become the limit as t approaches infinity of, and now we have 2 times the natural log of the absolute value of x, evaluated from x equals 1 to t. And then this is going to now become the limit as t approaches infinity of 2 times the natural log of the absolute value of t minus 2 times the natural log of the absolute value of 1. And then looking at the limit as t approaches infinity of our function, which is 2 times the natural log of the absolute value of t minus, and ln of 1 is just 0. This limit right here, because of our logs that we've looked at before, as t approaches infinity, this is going off to infinity, so this is going to diverge. And so we know that g, our g of x, diverges. We can say this diverges. So we just showed this diverges, but you could have also shown it just by looking at the definition that is on page 17 in our notes, and that would have been a faster way to do this problem. So always keep that in mind. And so since g of x diverges, and that is the smaller value that we have, the smaller function, we say that that's going to force our function f of x to diverge also. And that's because both f and g are continuous, and g of x diverges and it's less than our function f of x. So we'll say since f of x and g of x are both continuous and g of x diverges and f of x is greater than or equal to g of x, then f of x diverges also by the comparison theorem. And so we have one more example here that I'm going to go ahead and circle, and we will look at this one together in class.